Okay, well, I thought I'd make a video about Flux because I'm slightly obsessed with it, and well, it's just one of these things that I still want to get my head wrapped around completely, and have. But the more I teach it, the better understanding I get. And for this last bit of the semester, it's a huge concept along with circulation. And so you build up the theory from 2D to 3D, which is what we'll be doing in the weeks to come before we finish out the semester. And so if you really get a good understanding of it in 2D, I feel like 3D isn't such a stretch. So that's what this video is about. And there will be a homework problem here somehow on this that I still haven't figured out. But as I go through the video, I think I will. Okay, first of all, in 2D, flux is the measure of flow rate through or in out of a curve. Now the curve doesn't necessarily have to be a closed loop, but it's easier to think about it that way because you're really looking at the mass, how fast it's flowing. So if you have a closed curve, you can think about how this blob is exiting or growing based on the field you're working in. Okay, so we start off this buildup with a vector field. So let f of xy, which we'll call m sub xyi plus n sub xyj. So we're going to let be a 2D vector field. So we're going to let this thing be a 2D vector field. And I have a picture of one. This is just a random one. That's pretty, so I thought I'd use it. Okay. So here's my vector field, and each one of these little vectors has a direction and a magnitude, right? And if you take the function f of xy, say, and so here's the axes, right? So this is about, where are we at here? This is about 1. It's about 1. So whatever, f of 1, 0 is this little vector here in the field. So we start off with the vector field, and then we make our curve. So here's my curve. It's going to be a nice smooth curve here, like that. Okay, and this is some curve C. Now C is of course parametrized by, so R of t is going to be g sub t I plus h of t j, and t runs through some interval, and we traverse this thing. We're just going to go this way with it exactly once as we go around. And let's pretend that all these little vectors are some sort of fluid, right? And what we want to do is, let me get out of here. Done. Come on, go away. There we go. So what we want to do is see how much fluid mass exits this region. I'll call it D. Oops, come on. It's cool it went back to red. That's awesome. How much the fluid mass exits D in a quick moment, which is code for instantaneous rate of change, right? Calculus. Okay. All right. Well, let's look at the. So we're going to put some units in here. I didn't do this in the math part, but so let's just assume. Let's assume that the density is 1 kilogram per meter squared. That makes computations easier, right? Okay, so let's let the fluid flow briefly, i.e. a really small amount, delta T. And now I want to know, in this brief moment of movement, how much mass exits the region. We're doing exits, but we could have well done enter, or yeah. So let the fluid flow briefly, delta T, infinitesimal moment. What's the total mass? Exiting D, and that makes us go all the way around the curve. Okay. So I love this because, again, I keep saying the same thing over and over and over again through Calc 2 and 3 in particular. Each time you're just adding up something different, and each time it's the same sort of setup. So what I want to do here is, let's get this guy to come back. There we go. I want to take, where's a good one here? I want to take this little region here. Actually, it could be much smaller than that. And I want to magnify it hugely. Okay? Take one little piece of C. And here's a little chunk of C. I've just magnified it 200 times. Okay. Now I'm going to put the vectors in the field in red. Okay. And so here are, oops, that wasn't what I wanted. I keep doing that. There we go. Okay. So I'm going to take, there's one vector in the field. So this is f of some x1 comma y1. And then really close by, there's going to be another one. And because they're like right next to each other, like within 0.000001 centimeter of each other, they're parallel for all intents and purposes. And the length of these guys is what? It's v, where v is a vector from f, times delta t. Right? And basically it's measuring, so from delta t probably might get you from here to here. And it does the same thing from here to here. Okay. So the length of this guy is the vector v, which is from f, times delta t. And because delta t is so little, the length of this guy is tiny. All right. So also because this length is so short, we can assume this is sort of a straight line. And we'll call that delta s, which is a little chunk of the curve, right? And so, okay. This is the fluid. This is the mass leaving per unit time, right? So for one little delta t, this much liquid flows out, right? And again, we could have done the whole thing going in, but it's easier to go out first. And all the changes is the sign. And since the density is 1, The amount leaving is the area. Of this parallelogram. Okay. And so the question is, how do we find the area of a parallelogram? Well, we can go back to geometry here. And what you want is, if you run this line out here, you want this little height here, okay? And this is the part that I love, because now we get back to Calc 3. So this vector is the outward unit normal, and it's perpendicular to this, curve, which is so short it's actually a straight line. Okay. And so the height that we're looking for here to get our parallelogram height, this height is n dotted with v times delta t. Okay. All right, so what's the area of this little parallelogram? It is the width, delta s, times the height, which is n dotted with v times delta t. Okay. So in an instant, a delta t moment, this is the mass per unit time that's ejected from d. So if we divide out the delta t, we just get the mass, the actual amount that is left over time delta t. Okay, and this is v dot n times delta s. Okay, and again, this measures the amount of this amount here of liquid that has exited the region in time delta t. All right, so what we do is, let's go back to the curve. What we do is, remember that little delta s was, oops, come on, there we go, was just along here. So what do? We cut this into n of these, right? This is that calculus idea. Add them up, make it continuous, integrate, and what do we get? Let's check this out. Okay, right? If I add all these up, I wind up with, remember, v is just a vector from the field, so that's f. N is the unit normal, and delta s becomes ds, and we integrate this thing over the curve. And that's the flux integral. That's like the coolest thing ever. Right? So, at least in my little world. And the devil is in the details, right? So, because we're going counterclockwise, we put this guy here and make a little thing to show that we're going around the curve C, which is a closed loop. All right, well, let's look at an example. I want black again. Let f be the field x squared I plus yj. And let C be a circle of radius 2 centered at the origin, right? So r sub t turns out to be 2 cosine t I plus 2 sine t j, and t runs from 0 to 2 pi. Okay. So now let me do this. Yeah, I got it. Here we go. I'll make another picture. Where'd it go? There it is. So here is here's the center. It's a coincidence, believe it or not, that I chose 2 for the circle size. Why can't I see the whole picture? Damn it! There we. Oh, come on. All right, that's 2. So here's our C, and we're going this way around this guy. Now remember, earlier on in the semester, way back when we computed capped T, it went like that. And when we computed cap N, it went inward. But we want an outward one, right? And that comes around from the cross product. But if you're in 2D, you can just compute this guy the way we did in the past and take its negative, and that will put you going outward. So it's an extra step, but it's a lot better than doing the matrix to compute the cross product between, what is it, T and K? So we're going to do it that way and use our mad math skills. Okay, so here we go. First we have to parameterize the circle, then we have to find n, then we have to dot product, then we have to integrate. So let's do that. Wait, didn't we parameterize it? We did, okay. So now we have to find n. I'm going to rewrite it here. Cosine t I plus 2 sine t j. Okay. Take the derivative. It's minus 2 sine t I plus 2 cos t j. All right. The norm of v is what? Square root of 4 sine squared t plus 4 cos squared t, which is 4 times 1, and that's 2. Okay, so t equals minus sine ti plus cosine tj. It's just v over v. It's this. That's t. Okay. So now we compute dt dt, and it's minus cosine ti minus sine tj. I'm just going to put it over here. The norm of this guy is 1 because we're on the unit circle. And so that says n is minus cos ti minus sine tj. Here's that extra step, and I want to really explain this. If we take this n and go back to our circle, let's just pick t equals pi over 4. I'm going to go back up here. Go away. Why won't it erase? Oh, man. That sucks. Can't go back and erase? Anyways. Okay, so blue's not the right color. Let's do purple. And go back. Oh. Okay. So there's pi over 4. Now if you plug in, so there's the point on the circle. If you plug in pi over 4, you get minus 1 over root 2i minus 1 over root 2j, which is down here. So this is inward pointing, right? So the one we want is outward pointing because we're looking at flux. We're looking at the exit. So our n, which we're going to call n cap, is minus this, which is plus cosine ti plus sine tj. Okay? And that's our vector. It's the negative of this guy, because this one points in, and this one now points out. Okay? So let's do some calculus here. We have f dot n ds, which is the integral from t equals 0 to 2 pi f of rt dotted with n cap of rt times, oops, getting crazy here, times r prime of t dt, should only be one, and this is ds. We defined it that way earlier. Okay. F of RT is what? It's 2. So it's 4 cosine squared t I plus 2 sine tj n of RT is cosine ti plus sine tj and r prime is v, which is minus 2 sine t I plus 2 cosine tj dt. All right, and when you run all that out, you wind up with 2 cosine cubed t plus sine squared t dt. And then this you have to integrate. I think you get something like 4 pi, but this isn't too bad. This takes double angle, blah, blah, blah. Plug it into an integral calculator and get an answer. So this tells you the flow, the flux of this thing. And now if we had done the flux going inward, this vector n here would have had negatives assigned to it, and this would just be minus 4 pi. All right, so this is a chunk of homework 13, and I'm gonna really look closely at this one. We're gonna take this example, and we're gonna take this theory, right? The theory of this video, which, you know, is the most in-depth video I think I've ever made about flux, and I love it. And I think taking this argument and applying it to circulation will give you the, because we know from circulation that what? It's not f dot n, it's f dot t, right? This is circulation. So, okay, I don't know, take this example and the theory we just applied and explain to me why it's F dot T and what the circulation is around this circle in this field. And lump that in with homework 13. If you have questions, ask me in class.